This is the RGV Model Rocketry Podcast, a podcast about one of the most exciting hobbies on Earth, launching homemade model rockets thousands of feet in the air. If it's certification, building, flying, event coverage, competitions, organizations related to rocketry, we're talking about it. This is the RGV Model Rocketry Podcast, and this is Randy Ashley.
Welcome back to the Rio Grande Valley Model Rocketry Podcast. I'm Randy, and today we're going to be taking a look at high-power model rocketry. In previous podcasts, we touched on low and mid power. Today, we're going to be looking at high power, which is everything from an H motor up. And I guess the ceiling would be like an O motor because larger than that is beyond the scope of model rocketry. In previous podcasts, we talked about A through G motors. And actually, some of the largest G motors can be technically high-power rockets because they exceed the 4.4 ounces of propellant in the reload kit or in the motor itself if it's a single-use motor. Now, this is probably going to be a shorter podcast because there are a lot of small areas in high-power rocketry we need to look at, but we'll touch on those in individual podcasts to keep this one from getting too long. But the basics that we talked about in low and mid-power rocketry apply to high-power rocketry also. As I said, H and up are the classifications of the motors for high-power rocketry. Now, there's levels in high-power rocketry, which we may have touched on in the previous podcasts. Level 1 is the entry level to high-power rocketry, and that's going to be the H and I motors. Then level 2 is the next step up. For level 1, all you have to do is successfully fly a model rocket on an H or I motor, bring it back without any major damage, and you can be certified level 1. Level 2, there's a written exam, so you have to study, take the exam. Once you pass the exam, then you fly a model rocket on a J, K, or L motor, and then you can qualify for level 2. Level 3 requires a little more work because you have to document the build of your rocket. You have to come up with a plan and then work your plan. So you have to design the rocket, you have to simulate the flights so that you can show that the model rocket will be safe, that it'll leave the launch rod or the launch rail at a safe speed so that it can be stable, so that it is stable, so that the center of gravity and the center of pressure have the correct correlation between one another. The center of gravity should be forward of the center of pressure in order for the rocket to be stable. And we like to see about 2 times the diameter of the rocket between the CP, center of pressure, and the CG, the center of gravity. So if it's a 4-inch rocket, 4-inch diameter, then you'd like to see about 8 inches between the center of pressure and the center of gravity, with the center of gravity, as I said, being forward of the center of pressure. The easiest way to determine center of pressure is to get you a simulation software. There's many out there, so I'm not going to name them. Okay, I will. RockSim is one. OpenRocket is another. RockSim you have to pay for. OpenRocket is free. It's open source. And using that simulation software, you can determine where the center of pressure of the rocket is. Center of gravity, I prefer to make that calculation manually by seeing where the rocket balances. Certifying level 3 in Tripoli, once you've designed your rocket and you're comfortable with what you think you want to build, you'll run your design by a TAP member, Tripoli Rocketry Association. You should have 2 TAP members that are going to evaluate your design. The TAP members are not there to pass or fail you. They are there to provide guidance and help you along the way. They might make suggestions for changes to your rocket design. to make it more likely to be successful. Level 3 in Tripoli requires you to have fully redundant altimeters and ejection charge systems. So that includes redundant power supplies, redundant switches, and redundant altimeters. So one power supply or one battery and one switch can't operate both altimeters. Once your design is approved by your TAP member, then you have to document the build, TAP members, I should say. Then you have to document the build. What I mean by that is you have to have possibly some videos of you working on the rocket, pictures of you building the rocket, and several steps along the way as additional proof that you built the rocket and somebody else did not do it for you. So once the rocket's complete, the TAP members will do a final evaluation of it before the flight. If they give you the thumbs up, you fly the rocket. It has to be witnessed by the TAP member, and they will then sign off on your certification if it's successful. If not, at least you got to fly a level 3 rocket motor, have fun, and you get to do it again. So level 3 would be M, N, and O motor. It does get rather pricey when you get above an M motor. For a reloadable M motor, you're looking at around $300 to $400 for the motor case that the reload goes into, and then an additional $300 or $400 for the motor itself. Now, the good thing is the motor case is reusable as long as it doesn't get damaged. So for future flights, $300 to $400 for an M motor. And the price gets rather steep when you get above that. You can look up prices for N and O motors. I said this podcast may be a little shorter. The reason being, a lot of what we looked at and touched on in low power and mid power rocketry still applies to high power rocketry. Fins, body tube, nose cone. I explained a little bit about dual deployment. Most people who are flying for level 3 use dual deployment. Most people flying for level 1 and 2 may use dual deployment. It keeps the rocket a lot closer to the launch pad on recovery because of the fact that you're not putting out the large main parachute at apogee. High power rocketry also requires larger launch pad equipment because these rockets could be anywhere from minimum diameter rockets that a J motor will just barely slip into, and they're not too heavy, so the launch pads are not that large for those size rockets. But when you get up to an M or N motor, as an average, there are exceptions to every rule, but as an average, you're going to be between 20 and 50 pounds on the launch pad. So the launch pad needs to be able to support the weight of the rocket as well as remain stable in an upright position in winds and whatever else may cause it to try to tip over. Some of the igniters used in high power rocketry may require a little more voltage or amperage to ignite than some of the igniters used in low and mid power rocketry. So these are just some things to keep in mind when you step up to high power rocketry. Again, this is not an all-encompassing podcast on how to do high power rocketry, but just some things for you to think about, some things for you to look at as you think about your journey into high power rocketry. The National Association of Rocketry also has a similar pathway into level 1, 2, and 3 rocketry. I recommend that if you're thinking about getting into high power rocketry through the National Association of Rocketry, that you look up their pathway into high power rocketry at www.nar.org and look up certifications. I would rather you look it up and know exactly what the criteria are as opposed to me telling you and then telling you incorrectly. If you're thinking about going into high power rocketry through Tripoli, the website is www.tripoli.org. Look up the certification section and there'll be a guide there. There also should be a question pool that you can study for your level 2 high power rocketry exam. So as we discussed, and the move from low power to mid power rocketry, it requires larger parachutes. a little bit more robust build. When you step up into high power rocketry, that's even more so. Larger parachutes to support the heavier weight. You're going to have a more robust build, even more so than in mid-power rocketry, because the forces that are acting on the rocket are much greater than they were in mid-power rocketry. Remember when we discussed in some of the previous podcasts that when you go from an A to a B motor, the power doubles, B to C, C to D, it continues. So when you're going from mid-power rocketry, possibly a G motor, and you go to H, which brings you into high power rocketry, the thrust has doubled. And then from H to I doubled again. So you can see by the time you get up to an M motor, the forces acting on the rocket are quite substantial. Simply gluing the fins to the outside of the body tube may or may not be enough to have a successful flight without tearing a fin off. And once a fin comes off, the rocket goes unstable. The likelihood of the rocket surviving that is slim to none. And with the time and labor that we put into building these high power rockets, we definitely want to get them back and be able to fly them again and again. So we use more of the technique we call through the wall fin mounting. That's simply, instead of gluing the fin to the outside of the rocket, we slot the rocket body so that the fin can slide through the body tube itself, and the fin is glued to or epoxied to the motor mount inside the rocket. So you have multiple glue joints that you can put in there. You glue the fin or epoxy the fin, depending on what you're using, as an adhesive to the motor mount. And then there can be a fillet on the inside of the rocket body, and then another fillet on the outside of the rocket body. So as the forces are acting on the bottom of the rocket, it's not just pushing on the centering rings, it's also pushing on the fin root itself, where it's epoxied to the motor mount, and then it's transferring that force to the upper centering ring, and it's also transferring the force to the body tube itself. So the likelihood of a fly through, which is when the motor actually just flies through the rocket and comes out the top, the odds of a fly through are highly reduced because of all of the points of transfer of the forces passing that force to the body tube itself. It's also possible to put a thrust ring on the back of the rocket. Thrust ring would transfer the force from the motor pushing against the thrust ring out to the body tube itself directly. By the time you combine all of these techniques, you build a much stronger rocket. It's more common to see epoxy used as your adhesive in high power rocketry. If it's going to be a high speed rocket, it's very likely you'll see a layer of fiberglass applied to the fins. The fiberglass will go from one fin tip down to the base of the fin where it meets the body tube, around the body tube to the next fin, and then up that fin all the way to the tip of the next fin. This gives a tapered and layered approach and makes it less likely that the fins will vibrate or flutter. Fin flutter can rip a fin right off of a body tube, even with through the wall mounting where it's passing through the body tube down to the motor mount. It's still possible for that fin to be ripped completely off the rocket due to flutter. We could do a whole podcast on fin flutter alone. So like I said, we're just touching on the basics here, or on the high points. Now, going back to the altimeters and the ejection charges, one of the things to keep in mind when you're doing redundant altimeters and redundant ejection charges is you don't want both of the ejection charges firing at the same time. This could result in an overpressurization of the body tube and a rupture of the tube itself. So one of the ways we could do that is by using altimeters that give us the opportunity to set a delay. And we'll have one altimeter fire at apogee, and then the second one fire 1 to 2 seconds after apogee, so that if one charge doesn't do the job, the second charge hopefully will, but they don't fire at the same time. Keep that in mind when you're thinking about redundant altimeters for ejection at apogee. Another thing we need to think about in high power rocketry that we don't usually have to deal with in low power rocketry, possibly in minimum diameter rockets. In mid power rocketry, we may experience this, and that's high speed temperature ablation. We can experience some erosion of the leading edge of the fins or the tip of the nose cone due to the high temperatures experienced in mock flight, because these high power rockets, especially if you're using a large motor in a small diameter rocket, will exceed Mach. Some rockets exceed Mach 2. When we travel faster than the speed of sound, the heat builds up, especially on the tip of the nose cone, the leading edge of the fins, places like that. Those are some concerns that we need to deal with. Some of the nose cones actually have an aluminum tip on the very end of it. We don't like to use a lot of metal in rockets, but just the tip of the nose cone can be made from metal. Using substances on the leading edge of the fins that's more resistant to heat than just fiberglass alone is another possibility. I'm sure there's a ton of things I've forgotten about. If you have any questions at all on high power rocketry, you're thinking about getting into it, you want to know where to go, how to do it, you have some questions, give us a shout at our email, which is randy@rgvrockets.org, and I'll be glad to answer any questions that you may have, either via email, or if it's a good question, we'll actually put it on our next podcast, and I'll also be able to send you more information on links to the various websites and places you can get more information on high power rocketry. Well, until next week, we hope y'all will keep the pointy end up. We hope to see you next week. Well, actually, I don't think we'll see you, will we? We hope that you hear us next week as we begin our next topic. Pointy end up. We'll talk to y'all next week. This is Randy with RGV Model Rocketry Podcast.